Hello everyone, my name is Preston Rahim. I'm a junior in computer engineering at Purdue University, and over the course of this past semester, I looked into various artificial intelligence models of generating 3D models from 2D images. So an overview of what we'll be talking about today is the motivations and applications of solving this task of being able to create a 3D model from 2D data. The background information and some terms to define about 3D modeling and information that will make this process a little bit easier to understand. A description of a model I found that solved this very well. And when I re-implement that model, the results I got and what I learned there in the study and how the field can go forward. So some of the motivations for this are going to be that the fact that oftentimes we would like to solve problems that persist in our 3D world, and that usually requires to model them in a 3D virtual environment. Now, cameras and images are very widely available nowadays. If you have a smartphone, you have a camera on you basically at all times, and it's very easy to snap images. And as humans, we can look at those images and generally infer how they exist in 3D space. So if I see the side of a car, I kind of know that car extends out about a meter or so away from me on the other side, just because I've seen so many cars in my life. Now, training AI to be able to have that same sort of inferencing would take the necessity out of humans going into 3D modeling programs and doing that themselves. Some common applications are autonomous navigation for vehicles. So when cars are driving down the road, and many of them are starting to be more equipped with cameras, when they see other cars on the road, they're able to kind of understand how those cars exist in 3D space and make the necessary changes to how they drive. Another example that anyone can toy around with is Google Earth. So it looks at a bunch of satellite images from slightly different angles of the buildings, mainly from up top though, and is able to reconstruct them in a 3D manner. So here we have down here actually the Purdue engineering mall where this happened, and then rapid development of entertainment industry computer games, being able to take a picture of something and get a rough model of it in 3D before you go in and polish the details. Some background information to know is that 3D models exist very differently than the traditional 2D image. So whereas the 2D image is a grid of pixels where you just define every color in every different space, a 3D model is a more mathematical description of how that model should exist in 3D space, and therefore can be scaled up or down, and is very similar to vector art. So rather than just having a grid of XYZ pixels where you define where each one is filled in, you have equations that say there should be a certain arc that goes a certain distance at a certain angle that meets up with another arc and such like that. And that is where the differentiability challenge comes in. So going from 3D to 2D is a step called rasterization, and you basically take samples from the view you're looking at, and going in the opposite direction is non-differentiable with our traditional outlook on rasterization. It's very difficult for computers to infer those mathematical equations, arcs, and lines from merely a grid of pixels, even if those are coming from many different angles. So a model I found was SoftRas. It redefines the rendering pipeline to be differentiable by creating a probability map where every triangle in the 3D model has an ability to influence a given pixel. That allows it to go backwards and basically be a differentiable way of generating our 2D image so that we can go in the other direction. Colors are also sampled and used as aggregate functions to then put on the model. So some of my results when I re-implemented it on the ShapeNet database are very close, within 2 to 3 points of what they got in the paper, which I was very happy to see. And to bolster the paper's performance itself, it received 4 or 5 points higher than the other popular models at the time. So it was pretty effective at the job it wants to get done. And here is just a small example of what I was able to procure on my own machine. Here's a model of an airplane that I opened up in Blender. This is the object file, as you can see here. Going forward, lots of things I learned were that maintaining color detail and texture is quite difficult. It had to do with sampling of the colors it saw. Generalizing to different objects is quite difficult, and training does take a lot of time. And then going forward, improvements to be made were the fact that SoftRas is merely a rendering pipeline, and optimizing the neural network it exists in would make it far more efficient.